here to talk about gentle introduction to stream processing. I'm Nicolas Fraenkel. I've been working close to 20 years in technical roles in the Java ecosystem as a developer, as a team lead, whatever. And since 2 years, I'm working as a developer advocate. I work for a company called Hazelcast. You might have heard about Hazelcast. We have these so-called in-memory data grids. And if you don't know what is in-memory data grid, it's basically distributed data structures. So instead of having your, for example, your hash map inside a single JVM, then you can replicate or you can shard the content over different nodes on the network. We also have something called Hazelcast Jet, which is in-memory stream processing. Since I will talk about it a bit later, then I will go no further right now. Our schedule is pretty tight. First, I would like to tell you why streaming, to set the context. Why are we in a world where we right now do streaming? Then I will tell about different streaming approaches. I will have a little bit of focus on Hazelcast Jet. Then I will talk about OpenData because I want to show you a demo, and for that I need some data. And about a specification, because the demo will be about showing the public transport in Switzerland over a map, and for that I need a standard. I mean a data format. And then I will finish with the demo if time allows. So in a time before our time, when I started working 20 years ago, all data was stored in SQL databases. All data. There were talk about object-oriented databases. There were still like all databases that were not SQL, but I mean all companies were storing their data in SQL databases. But even at the time, there were use cases where basically SQL was not a great fit. For example, the analytics. I've worked in retail and in general, at least in France, on supermarkets directors or perhaps head of departments, they want to know their sales in the previous hour. So they could adjust their promotion, their discounts accordingly. If they didn't sell enough regarding one stuff, then they will promote it and announce a discount for the next hour. Also about reporting, you probably have a bank account. You know that every month or every year or both, you receive the detail of the operations that took place on your account. And in both cases, it's not really great to have SQL. And the reason for this is SQL is basically good for normalized data, for data where you write. And because then you want to put constraints on your write so that when you read, you are sure that it will be in this format. So SQL and constraints, they make sure that the data in which you write your data is correct. The problem, those constraints, they have a cost, they have a performance cost. For example, in general, you would say that a good SQL database implements up to the third normal form, meaning that you don't duplicate data. And no duplicate means that when you query, you join. And you know that if you join over multiple tables and your query return a lot of results, then it will have basically a performance impact. So SQL and constraints are good when you are writing, but if you are only reading, then it's not that great. And analytics and reporting, it's all about reading. So because of those different actors, those different use cases with different needs, we needed an ETL, extract, transform, load, because it was not a great idea to use the same database to do the writes and the transactional reads and the analytics reads at the same time, because that would put too much pressure on the same database. And you wouldn't want to have performance impacts on your transactional database just in order to do analytics at the same time. And so came the batch model. And the batch model was about reading data from your transactional database, transforming it in general, denormalize it, and load it into an analytics database. And I believe that even if you don't have a lot of experience, you have seen batches already, because batches, they are everywhere. I mean, small companies, big companies, whatever, the sector, public administration, retail, banking, everywhere. Every company uses batches. And again, because you probably have seen batches, you know that the batches, they have two main properties. The first one is they are scheduled at regular intervals, whatever the interval, daily, weekly, yearly, whatever. And they run into a specific amount of time. And at the beginning, everything works fine, because in general, when you start a new batch, you start with a fresh database, and so the data is pretty limited. But bad stuff happens because we work, well, in the real world. And what is the bad stuff? Well, the data grows and grows and grows and grows over time, so that the time it takes you to execute the batch grows as well.
Hey, Nick, to interrupt you. Are you already screen sharing? Because we can't see your screen.
That's a good stuff. I thought I was screen sharing, so I'm very sorry about that.
Oh, now we see you. Thanks.
Sorry, thanks for the mention. I thought that, I mean, going from the back room to the main room, unshare my screen. Sorry about that. Anyway, I hope you still like the first slide, or the slide of my face. Anyway, so about the batches, the execution time over time might overlap the next execution schedule. So if you run your batch, well, if you schedule your batch to run every hour, but your batch takes 1 hour and something, then it gets harder and harder to run it in time, because of course the window won't grow over time. Another issue that can happen is, again, because the amount of data grows and grows, at some time you might have too much data to handle in one chunk. What happens if the batch fails mid-execution? Imagine it's still okay. Your batch runs in 40 minutes and it needs to run every hour, but now it fails at half an hour. Do you still have more time? Do you still more time to restart it? You've got this kind of issue with batches. So regarding the failing mean execution, you could have chunking, and then you keep a cursor, you only manage a chunk of the data and you manage it chunk by chunk. And basically in that way, you minimize the risk of restarting from the start. You restart from the cursor left. But then you've got a new interesting problem is, what about new data that came in between? But the main issue is about parallelization. With most old legacy SQL databases, it was just primary node and then fail over secondary nodes if necessary. So if you wanted your SQL server to be faster, to manage data faster, then the only thing you could do was vertical scaling. You added more CPUs, more RAM, more whatever. And we all know that at some points you reach a limit. There was no way to scale horizontally. So 10 years ago, perhaps 15, at least 10 years ago, there was this big movement on big data. And these big data movements had two main goals. The first was about running things in parallel, and mainly it was achieved through MapReduce. And then because you can run things in parallel, you can scale horizontally, and scaling horizontally is much easier to do. And the second was about NoSQL. And it has a different it was a different mindset. A lot of people were focusing on the negative aspects of SQL and saying, hey, those constraints, they cause a lot of issues. We need to be fast. We cannot have so many constraints. So let's remove all constraints, and we don't care about joins. We put the whole data, we duplicate the data, and then we can read like super fast. Of course, it's always like that. When you go on too much one side, then afterwards you have a counter movement and you go well over the other side, because we all know that was perhaps not the good trade-off, but at least at the time it was like that. And we moved from a schema on write, where you enforced how data should be written, to a schema on read, when it was up to the reader to assume, to know, to infer what format the data was in, and to handle potential errors, because since you had no constraint on write, you could introduce badly formatted data. But now we are even one step forward. Now there are a lot of people or companies or systems that look at everything like it's an event. Like you might have heard about event sourcing. Everything is an event. So we should think about events. And the good thing about an event is it's much smaller in scope. It's independent. And so if we can make everything event-based, then we have a lot of benefits. First benefit, it's memory friendly. You don't need to load your whole database in memory before processing it. You just like load one event, and an event is very small. For the same reason, it's easily processed. And another benefit is that it's pull versus push, because when you are doing batching, you're actually like pulling data from one place to the other, whereas with event-based, in general, it's directly pushed into you. And because it's pushed as soon as it arrives, as soon as it's generated, you will be close to real time. There is no such thing such as real time. It doesn't exist, real time, but close to real time or near real time is achievable. And then you can see your events when they aggregate, whatever you do with them, as being derived data of your data source that generates them. If you have been working in Java, you might have seen that just inside the scope of the JVM that before we were dealing with collections, and collections were finite. Your lists, your map, your whatever, you could count the number of items they contained. There might have been millions, but they were finite. And with Java 8 streams, you are able to create infinite streams of events. I need to mention also stateful streams, because once you generate events and you have streams, you might not only want to act upon each event individually, but you might want to do some aggregation. In general, you might want to have the average. The analytics before that I mentioned was you wanted to get the sum of all sales in each department, for example. And when you want to do aggregation, then you've got this new concept of window. So over which time frame do I want this aggregation? And when you start thinking about windows, there are different ways to think about windows. They can be fixed. So let's say you have the window that starts at each hour and lasts for 1 hour, or you could have like sliding windows, and then you say, oh, the window it starts at this hour, but then I need to count it again like after like 1 minute or 5 minutes or 10 minutes, and then the window they are not just separated, they slide over each other. Anyway, streaming can be seen as a smart ETL. So you have like sources of events and you have targets, and it can be anything. And meanwhile, you have this transformation pipeline that you can do. And of course, you can combine multiple streams, you can enrich the streams, you can do whatever you want like before, like in the Java world, you can map, you can filter. The good thing is, since by default, most of those stream processing engine, at least in theory, they can be parallelized, then you can distribute them all over the network, those computations, and scale horizontally as much as you want. And with that, you can have really, really nice side effects. You can have those like close to real-time dashboards, like the sales, for example. Think about it. Before, you had those batches, and the batch, again, for the sales results, they had to be run at each hour. Now, if you wait until the hour has finished, it still takes a bit of time to run the batch, perhaps 1 minute, perhaps whatever. But that means that you don't have the results up until the hour plus the time it takes to execute the batch. Most of the time, you will have the exact result that you wanted. Well, I hope more than most of the time. All the time you will have the exact results, but it lags behind. And in general, decision maker, they would prefer slightly wrong data, but as soon as possible. Because the number of cells, I mean, they might be not correct 5 minutes before the hour, but they already give a good feeling of what happened. So perhaps it would be better to have the numbers 5 minutes before the hour, or perhaps even 10 minutes before the hour. And so when you've got streaming, you got the data as soon as it arrives. It's aggregated as soon as it arrives, and you can see the trending in close to real time. And right now, the machine learning stuff is super hype. Now imagine you've got this like trend that comes in, and you can train a machine learning model with it. Then you can have some very cool stuff done. And again, 10 years ago, I don't know if you remember, if you are that old like me, there was this kind of stuff called complex event processing. At the time, there was not stream processing. There was something called enterprise service bus. So the idea was you would have a single bus in your company, and every software component will like put their events into this bus, and some other components will listen to those events. I don't know why, but it was, at least I've never seen any successful implementation. But the idea was, by combining some of those events, some downwards components would be able to infer some things that happen to your system. Well, here it's the same. You can have complex event processing, because if you combine some of the streams, then you can make something out of them. Now that we have those events, we need to have some way to process them. And the first way to process them is, first we store them. And right now, you might have heard, I hope you have heard about Kafka, because Kafka is super widespread, is ubiquitous. Everybody talks about Kafka. You might have heard also about Pulsar. Pulsar seems to be a competitor. They are both hosted by the Apache Foundation. I don't know about Pulsar. I don't know much about Kafka either, but you might take a look at Pulsar. For example, for scaling the number of computing nodes, it seems to be much better than Kafka, because Kafka needs rebalancing. Anyway, Kafka, the good stuff is distributed. It persists the data on disk, which is a good thing and a bad thing. The good thing is, because it persists the data on disk, if something crashes, the data is still there, you can still use it. Now, the bad thing is it persists the data on disk, meaning that every time you need to read or to write, you need to access the data on the disk, which is an expensive operation compared to in memory. So on the other side, you have those in-memory stream processing engines, and those are based on the fact that you don't require to have a disk-based approach. Some of them are on-premise, such as Flink or Jet, that I will talk about it later. Some of them are cloud-based, such as Kinesis or Google PubSub. A special mention for Apache Beam. Apache Beam is an abstraction over some of those I mentioned above. And the good thing is, if you are a bit worried about vendor lock-in, then you can use Apache Beam on top of your implementation. You interact only with the Apache Beam API, and then you can plug, unplug, and plug a new stream processing engine. Of course, it's not as easy as it's said, because not all stream processing engine work in exactly the same way. There is no standard for stream processing. So there might be some different ways of doing things, and you might have bad surprises if you unplug one that is not super compatible with the new one you plugged. Anyway, if you are a bit worried about vendor lock-in, that can be an easy way to manage that. Let me say a few words about Hazelcast Jet. So Jet is an open source stream processing engine. It's a single jar. So if you are in the Java world, it's really cool. You just use it as a dependency and you start it from here. And it has a unified batch and streaming API, meaning that if you are not comfortable with streaming yet and you prefer batching, you can use Jet with the standard batch. And then you just add one line of code, and then you make your first step into the streaming world, meaning that it's unbounded data. Of course, we have an Hazelcast Jet offering, but I won't talk about it, and whatever is in the demo is completely open source and free. Stream processing engine in general have those two concepts. They can be named differently in their own ecosystem, but in Jet we use the name pipeline, and pipeline is the code you write. It would be like akin to Lambda, Java lambdas. So it's declarative code. You tell where you will be reading from, you tell about the transform, you tell where you'll be writing to. And then when you have written your code, there is a client. It takes this code and it sends it to the stream processing engine. And it's the stream processing engine job to run it. And the stream processing engine knows about the topology, knows how many nodes, whatever the cluster is, and it's his job to route it all over the cluster. There are two deployment models. The first time, as I mentioned, is a single dependency, a jar that you can embed in your application. And since Jet leverages the Hazelcast IMDG, as soon as you start a new Jet instance by calling jet.newJet instance, by default, if you didn't configure it further, it will broadcast over the network, find other nodes that are already running, and they will begin to form a cluster. That is the easiest way to start with, and it works very well. But there is a downside. In general, the workloads of your application and the workload of Jets are different by essence, meaning that the configuration of the JVM might be put at odds between optimizing for your application or optimizing for the cluster, which is not that great. And also, if you want to scale horizontally, well, your cluster will scale horizontally along with your application. In general, it's the other way around. Your application will need to scale horizontally along with your cluster. So we have another deployment model. We create a dedicated Jet cluster. This is the client-server mode. And for that, you can use the command line, but in general, nowadays, you would use a Docker image. And we have mcharts if you're using Kubernetes. And then you have your application that uses a dependency that only has the client API. And on this client API, you can do the same, but you can see instead of creating a new Jet instance, you say a new Jet client, then it will connect to the cluster. The other benefit of this approach is that we have bindings for languages that are not Java. So basically we have C#, we have C++, we have Go, we have Python, we have Node.js. So in that case, you can use the benefits of Jet without being bound to the Java technology stack. So this is a bird's eye view from Jet. It's just an implementation of what I've shown you before. you've got sources, you've got sinks, and then you've got these transformation stuff in between. Two things that I need to mention. If you know about change data capture, the fact that you can listen to events made to your databases, we have an implementation of change data capture through the Debezium. So if you want to create events out of state, so event sourcing is you create the state out of events, you aggregate events and you create the state. Change data capture is about just the opposite. You create events out of the state, so we can do that. If we have an API to create new connectors, so if there's something that doesn't exist here, for example, in the demo I show how to connect to a web service, I created a custom corrector. And the third stuff that I need to mention is when you need to enrich, which is in general the case, your events, they are not self-contained. In general, they might contain IDs, and the ID you need to inflate it. You need the whole entity that is referenced by this ID. If every time you need to inflate it and you need to go to a database, then you're just, again, reading from disk, and you're just not using the streaming way to its fullest. You will lose performance. In general, what you do is you preload your entities in memory, and then everything is in memory, and you can combine them from memory. And this is what we will do in the demo. And here shines the power of Hazelcast Jet and Hazelcast MGG together. As I mentioned, it's the responsibility of the stream processing engine to distribute the workload, not only over the cores of a machine, but over the nodes on the network. And if you know that an operation cannot be distributed, it might be the case, then you can, in the API, set that this cannot be distributed, and it will run on a single node and on a single core. I need to mention OpenData because now we have streaming. I hope that I made it clear what streaming is. But streaming is about data, and if we have no data, that's not that interesting. I believe that you're working for companies that have a lot of data, but all this data is private because that's the value. Most of the company's value is the data they hold. So I wanted the demos, so I wanted to use some data. And in the realm of data, you have this open data, and this that open data movement is to data, was open source is to software. So it's free data that you can freely use without patents, without copyrights, without anything. I'm French, I work in Switzerland, so I know about initiatives in France and Switzerland. I understand that Germany is also very, very pushing toward open data, but about the European Union also has an open data initiative. If you're elsewhere in the world, I know less about it. I've stumbled upon in California, there also seems to be some open data, a government-led initiative. Open data is no free lunch, however. It's not because data is available that it's fun to use it. And here are some of the challenges I faced while trying to leverage my open data. The first is access. If you are a developer, you believe that all data is accessible through a web service. Well, it's plainly wrong. Most administration, they give you data in the form of a file. So you need to download a file, which is not that great because you don't know how frequently it will be refreshed, or if they even tell you how frequently it will be refreshed. Not fun. Second issue is you might believe that open data means open format. I'm not even talking about Microsoft old legacy formats in binary form. I'm talking about, hey, did you ever try to get data out of a PDF? It's no fun either. Third issue is about the standards. Imagine that we are using XML, no YAML, no JSON. We have XML, so something that was made for that. The question is, which grammar is used? Do we even have a grammar? So we probably need a shared standard that is like focused on a single domain. And you might know this XKCD comic where somebody say, oh, we have those 14 competing standards. I will create my standard to wrap them all. And at the end, you have 15 competing standards. Doesn't work that well. Final challenge, data scientists, they complain that they are spending 80% of their time curating the data. Where if you are a data engineer, it's the same. And this is from the demo that I will show you. The second and third columns are supposed to be time. So I know what 16 hour, 20 minutes is. I have more problems with 25 hours. What does it mean? What should I do with it? Should I ignore those results? Should I say, oh, it's also the same day, but it's 1 a.m. or it's on the next day, 1 a.m. I have no clue. Fortunately, I overcame all those problems. And as I mentioned, I want to show you a map of all public transport. So I need a specification, and I stumbled upon the general transit fit specification, which I believed wrongly that was a public standard. It's not public standard. It's one that is proposed by Google, to the point that I thought it was the Google transit fit specification, but it's general. However, they might have changed it in between. And GTFS is based on two different things. First, you have static files, stuff that is not supposed to change frequently. For example, the stops. You have a bus, the stops, they might change over time, but not frequently. So the thing is, you get the static model beforehand. I won't talk about any each of them in detail. Just need you to understand that there are files and they describe the static model. And then you have this full-fledged dynamic model. You read this model, so you call probably a web service, and then you get this model. And you see here, the root message is the feed message. There is a one-to-many relationship with a feed entity, and there is a chance you get the vehicle position, and you're done. It's easy. So I thought, wow, that's cool. Let's use that. There is a provider of OpenData in Switzerland regarding the public transportation. It actually implements the GTFS. That's the reason why I'm talking to you about it. As I mentioned, you first download the files as text file, and then you have a dynamic REST endpoint that you can query. And the first time I got the REST endpoint results, I got this model, which is very different, which is a very strict down version of the whole model that I was expected, especially where is the position. And that's the problem. Actually, I don't get the position, because to have the correct position would probably mean to have GPS chips on buses and the trains, and it wouldn't be so privacy friendly. So instead, what they provide is they provide you with a timetable in the static file, and then they provide you with trip updates saying, oh, this bus here it will be at this stop and it will be on time. Or this bus at this stop, it will be late by 2 minutes. And now comes the real problem, the real power of stream processing is because of this pipeline, I can compute that in a perhaps not easy, but at least not too complex way. And this is my pipeline in the end. So I read from the web service. I have a huge JSON payload. So I split it into trip updates. And every time I do some enrichment, as I mentioned, those trip updates, they have an ID that reference something that is in a static file. And when I will want to read, I will want to read the data, and not every time I read, have to join it with something else. So when I do my stream processing pipeline, I do this enrichment with the trip data, with the stop time. Also, my front-end developer wanted me to have timestamp instead of hours. And at the end, I put everything into memory, into Hazelcast IMDG. And now I will start the local jets. I will start to load the data because it might take a bit of time. And meanwhile, I will continue my presentation. And this is the architecture overview. I have this Hazelcast Jet cluster, and in my demo, there will be a single node because, of course, my machine is only so big. I have a loader job, and this loader job, I will submit the job to the Jet cluster, again, single node. It will transform it, sorry, I will send the pipeline, it will transform it into a job. And the job will be to read each of those files and put them into this IMDG dedicated map. So each of those files, they will be on a map. There will be a routes IMAP, there will be a trips IMAP. Then when everything is finished, I will have this loader, which is another client that will send the pipeline and create this job load dynamic. And the goal of this job is to call the REST endpoint. And I have a constraint. The constraint is I cannot call the REST endpoint more frequently than once per 30 seconds, because otherwise there is rate limiting implemented on the OpenData endpoint. And if I call it more often, then I will get a 429 HTTP status. Then I will get this dynamic data. This dynamic data, I will process the pipeline that I've shown just before, this pipeline, and I will store the results into IMDG. And then finally, I will have a web application that registers to changes made into this map. And when there is a change, it will put it into a WebSocket queue. And finally, I will have a JavaScript on the front end that will read this queue and process it. How does it look like finally? So here, how long do I have? I have still a couple of time. The most important place here is the structure. So I have this load static module. It's made, well, to load the static file. I have the stream dynamic, and I have the web application. Here, I want to show you at least the processing pipeline, because it reads a lot like the slide I showed you before. So I have this main method, this is Kotlin, this is not Java, but I believe that you can still read it. As I mentioned, here I'm using a client-server architecture, and I will send this job, this pipeline, as a job. And the pipeline maps exactly the slide that I've showed you before. So you will read from a service, you will flat map the payloads by splitting the payloads. Then I will enrich it with the trips. Then here I have a slightly more complex enrichment to do. So I cannot just say, hey, enrich it with the stop time. I need to do something. And then I will map the hour to timestamp and again. And at the end, I will write everything into this update map. And perhaps now it's not finished, so we need still to continue. I will show you how I can split the endpoints. So everything that I can do is function. So it's if you are used to functional programming, then it's functional programming. I get the payloads, I transform it to a JSON object, and then I get the header, I get the timestamp, and I get the entity that was passed to me, and I return this trip traverser. So everything is about transforming the data that arrives. And here there is this example of enrichment, but of splitting. But here you can have some kind of enrichment. Here, you just need to understand how you extract the ID from the JSON entity. And now it's taking a bit too much time. I don't remember when I started it. So because time is running, I will just show you the movie. And this is at the end what you will be able to see. Sorry. So this is the map of Switzerland, and you can see that I've already loaded everything. Sorry about it not being the real demo, but time is running and I don't have time to load everything. So you can see the names of the stops. You can see here the red means it's a train, the green means it's a bus. You can see it's like running over its course. And the problem is, since I don't have the real location, I need to interpolate between two stops and their planned arrival time. You can see them moving all over their routes. Another issue that I have is I only have the GPS location, so sorry, the longitude and latitude of the stops themselves. So I need to draw a line between them. You can see they are not running exactly on the exact roads, but it still gives you a pretty rough idea of how it could look like. And this, I believe, is a pretty cool data visualization example. Let me get back to my demo, to my slides, sorry. So in this talk, I've shown you that streaming has a lot of benefits. However, streaming is useless without any data. So let's leverage OpenData. If you want to leverage OpenData, be very careful. It's really like the Wild West. You need a lot of time to understand the shape of your data, what problems you might have. And you need time to understand how you could curate it. But if you manage to do that, you can get very cool stuff done. Or I hope for me, it was cool. Thanks for your attention. You can read my blog. You can follow me on Twitter. If you want to learn more about Jet, we have a website. If you want to learn more about GTFS, there is a dedicated website. And more importantly, if you want to do the demo that I had no time to show you at home, then here there is a GitHub repository. I took time to write a very, very long README. So if there are any issues, just please ping me. And now perhaps there are questions. Any question? You have explained how you can feed the updates into the system, but how do you get the initial data stock? So the states on which to apply the updates. I'm not sure I understand your question, but here I can show you where I get the streaming endpoint. So I will stop that because it takes all of the resources on my machines. Here, for example, I'm reading from the remote service, and this is how it looks like. This field buffer function actually is the one that reads. Here you have a word so that you can ignore. It just made so I cannot read more than once per 30 seconds to prevent this 4 to 9 error. But I'm just just making a GET request to the URL that I configured with the authorization token. And then if it's okay, then I get the JSON. I just get the results that I have, and I put it into a buffer. And this buffer is provided me by Hazelcast Jet. And it's up to Jet to handle it afterwards downstreams. So my goal, my responsibility is just to read data wherever I want data to be read, and then put it into this buffer. And afterwards, I write my transform and my targets or whatever. Another question, how do you control having several nodes of a listener service so that the message is not received by more than one service? So that's a very good question. So imagine here I only have one node over a cluster. How do I manage to have only one node that is reading? Because if I make multiple requests to the same endpoint, I will have duplicate data. It depends on the system. Here, I only have one node. That's not an issue. Another thing could be, hey, you could have a lock that says, oh, this node is reading, so no other lock is reading. And Hazelcast IMDG provides a shared lock system. So it could be another way to do it. What you could also do, not in this case, is you could have a processing pipeline that is able to handle duplicate messages. So you could get a list of all message IDs that were previously processed, and you could check whether it was processed by reading into memory, for example. Again, IMDG, you have a dedicated map, or you have all messages that were already sent and processed. You say, oh, I found it, so I don't need to process it. There are multiple ways to do that. With every one of them as trade-offs, like every time. So there is no real good answer, but here are at least 3 alternatives that I mentioned. Other questions? Oh, I hope I answered the questions correctly. What is the right way of handling errors during processing of events in case if everything is in memory? That's a good question. I guess that by errors, you mean like exceptions, or you mean by errors, meaning a node fails? If it's the first case, well, you have your usual try, catch, or whatever, and then you need to handle that by yourself. If it's what if a node fails, then of course it's not your responsibility. And Jet has the concept of snapshots. So every now and then it takes snapshots. So if a node fails, the processing of the data should be distributed. Again, here, one node, in general, multiple nodes. So if a node fails, that's not an issue. And the more nodes you have, the less failure of the whole system, of the overall system, the probability is lower in that case. So we have snapshots, and we can restart from a failing node.
So you store events somewhere, huh?
Yeah, we store events in memory. And again, we store events in IMDG. So IMDG is distributed. And as Jet leverages IMDG, we have as many IMDG nodes as Jet nodes, or the other way around, if you prefer. So if you have 10 nodes and you have a replication factor of 3, that means that you need to have 4 nodes that fail, at least to be sure that one node you will lose data. So the more replication you have, the safer you are. Of course, the slower it will be in the end. I mean, again, it's a trade-off. Did I understand your question correctly? Did I answer in the way you want?
Yeah, for sure. Thank you very much.
Thanks. What are the main advantages of Jet compared to Apache Flink? That is one of my favorite questions. We are the best, and they don't compare to us at all. No, I cannot answer that in a really good way. It's like asking a BMW vendor, hey, how do you compare to Renault? What are your main advantages? I mean, you cannot trust them. So whatever I tell you, there is no way in hell you can trust me about it, because of course I'm super biased. Also, to be very honest, I don't have any experience with Apache Flink. And yes, we are competitors, that's for sure. I would suggest, if you're interested in that, to have prototypes in both cases and to check whether any of them fits your use case. What about logging in Hazelcast Jet? It depends what you handle by logging. Here, for example, I have used something called peak, and peak was just a way to write in my std out. So here you could have this stuff, but we delegate to any logging, well, any standard logging framework you want. So you could have, for example, asynchronous logging, which means that despite logging and writing to disk, we don't slow down your pipeline. Of course, if you are much, much faster, the pipeline is too fast for too long, messages will be lost. But if it's this kind of logging, we can catch up. You can configure it. I think it's SLF4J. I'm not so sure about Log4j 2, but SLF4J has this concept of asynchronous logger, and it has a buffer, and you can keep your stuff in buffer. Any plans to have integration with AWS? Yes, we have plans to integrate with AWS. Right now, we have an Hazelcast cloud offering. This is not open source, but there is a free tier, so you can try it for yourself. And of course, the next step will be for Hazelcast Jet to run on the cloud. So I don't need to do that on my machine, but I can show you something that is already prepared. Any plans to have a reactive library? That's a very good question. We are thinking about it. We are a small startup. We cannot do everything. Right now, we have asynchronous API. We already know how to do asynchronous. So in case you want to do that, you are more welcome to integrate your reactive stream or React or whatever with our asynchronous API. I just recently wrote a blog post how you could migrate from annotations to reactive and to be sure to be non-blocking. But yeah, as I mentioned, our resources right now are strained. We cannot do everything at once. So we have plans for sure. However, I cannot commit to a date, unfortunately. If you are interested, however, it's an open source project. We welcome contributions. Last year, during Google Summer of Code, we had 2 students working on our code. So I don't know whether you are a student or not. I don't know how much time you can commit, but if you have good plans and, well, a design in mind or something, we have a Slack. So join the Slack, talk with the developers, talk with the people who have plans, and let's make something awesome together. Well, thanks for your attention, and I wish you a good rest of the conference. Enjoy the other talks.